The memory horizon. What reality forgets and why it matters. In September 2019, a physicist at the University of Geneva made an error that should have been impossible. Dr. Nicholas Giesen, one of the world's leading experts on quantum mechanics, a man who had spent 40 years studying the foundations of physics, was reviewing calculations for an experiment on quantum entanglement when he noticed something that made his hands freeze on the keyboard. The mathematics was wrong. Not his calculations, the mathematics itself. The equations everyone had been using for decades to describe how quantum systems evolve over time contained a hidden assumption that, when examined carefully, violated the most basic principles of logic. The assumption was simple, seemingly innocent, that real numbers, those infinite decimal expansions we use to measure everything from distance to time to probability, actually exist in physical reality. But real numbers require infinite information to specify precisely. The number pi, for instance, has infinitely many decimal places with no repeating pattern. To store pi exactly would require infinite memory. And the universe, as vast as it is, has only finite memory capacity. Giesen had discovered something shocking. The mathematical framework we use to describe reality assumes reality can remember infinitely many details about its own state. But physics itself, through the holographic principle and the Bekenstein bound, proves that the universe has finite information storage capacity. This means the universe cannot be doing what our equations say it's doing. Reality cannot be computing with real numbers because real numbers require infinite memory, and finite systems cannot store infinite information. Something fundamental was wrong with how we understood time, causality, and the nature of physical law itself. What Giesen had stumbled upon was evidence of a phenomenon that would transform our understanding of existence. The universe forgets. Not metaphorically, not approximately, but fundamentally, continuously, unavoidably. Every moment, reality discards information about its own past. Every quantum measurement erases possibilities that once existed. Every passing second pushes details beyond what physicists call the memory horizon, the boundary between what the universe can remember and what it must forget. And this cosmic forgetting isn't a flaw in the universe's design. It's what makes time flow. It's what makes causality work. It's what allows the future to be genuinely different from the past. Without forgetting, there would be no time. Without information loss, there would be no change. Without the memory horizon, reality would be frozen, perfectly deterministic, completely reversible, eternally static. Today, we journey through evidence that reveals reality itself has amnesia, and why that amnesia is the most important feature of existence. We'll explore how forgetting creates time, how information loss generates free will, and why the universe's finite memory might be the solution to the deepest mysteries in physics. What you're about to learn will change how you understand every moment of your existence, because every moment is an act of cosmic forgetting, reality choosing what to remember and what to release into oblivion. We begin. Act 1. The Discovery. Nicholas Giesen's revelation began with a simple question that had troubled him for years. How does quantum indeterminism actually work? Quantum mechanics tells us that before we measure a particle's position, it doesn't have a definite position. It exists in a superposition of all possible positions simultaneously. When we measure it, the superposition collapses to one definite outcome. But when exactly does this collapse happen, And how does nature choose which outcome to actualize? The standard answer, the Copenhagen interpretation, taught in physics classes worldwide, essentially says, don't ask. Measurement causes collapse, the probability of each outcome is given by the wave function, and that's all we can say. The moment of collapse and the selection of outcome are fundamentally random, beyond the reach of deeper explanation. Gisin wasn't satisfied with "don't ask." He began examining the mathematical structure of quantum theory with uncomfortable attention to detail, and he noticed something peculiar about how time appears in the equations. In classical physics, time is a continuous parameter, infinitely divisible, flowing smoothly from past to future. We represent it with real numbers: 0, 0.1, 0.001, 0.00001, continuing forever with arbitrary precision. Quantum mechanics inherited this representation. Time in quantum equations is a continuous, real-valued parameter, just as in classical physics. But here's the problem. If time is genuinely continuous in physical reality, if infinitely many distinct moments exist between any two time points, then the universe must track infinitely much information about when things happen. Consider a simple quantum measurement. An electron's position is measured at time t. The precise value of t, if it's a real number, requires infinite information to specify exactly. The universe must know not just that the measurement happened at approximately 2:30 p.m., but at exactly 2:30:15.39482746103827 p.m. with infinite decimal places. This seemed absurd to Gisin. The universe would need infinite computational resources to track all those decimal places. It would need infinite memory to store the precise timing of every event. But the universe demonstrably has finite resources. The holographic principle, one of the most robust results in theoretical physics, proves that the maximum information content of any region of space scales with its surface area, not its volume. For the observable universe, this implies a maximum information capacity of roughly 120 bits, enormous but finite, not nearly enough to store infinitely many decimal places for every real-valued quantity in physics. The mathematics we use to describe reality requires infinite information, but reality itself has only finite information capacity. Something had to give. Gisin's solution was radical. What if time isn't actually continuous in physical reality? What if the real numbers in our equations are just approximations, useful fictions that make the math tractable but don't correspond to genuine features of nature? What if the universe, at its most fundamental level, operates with finite precision? What if reality computes with numbers that have finite information content, what mathematicians call computable numbers or rational numbers? This would mean that between any two moments, there aren't infinitely many intermediate moments. There's a finite, though perhaps very large, number. Time wouldn't be infinitely divisible. It would have a finest granularity, a smallest meaningful interval. And crucially, this would mean the universe must constantly round off its calculations. It can't track infinite precision, so it must approximate, discard details, forget information. At first, Gisin's colleagues dismissed the idea. Surely we'd notice if time weren't continuous. Surely quantum mechanics would fail if the universe couldn't compute with real numbers. But Gisin showed that for any practical experiment, any measurement we could actually perform, the predictions of finite precision quantum mechanics are indistinguishable from standard quantum mechanics. The difference only appears in situations requiring infinite precision to distinguish, situations that, by definition, are experimentally inaccessible. The universe could be operating with finite precision, constantly forgetting information, and we'd never notice through direct measurement. But we would notice through indirect consequences, and those consequences turned out to be profound. If the universe has finite memory and must constantly discard information, then several puzzling features of quantum mechanics suddenly make sense. First, quantum indeterminism. In standard quantum mechanics, measurement outcomes are fundamentally random. We can calculate probabilities, but we cannot predict which specific outcome will occur, even in principle. This randomness has always seemed mysterious. Why would nature be fundamentally probabilistic? But in finite precision quantum mechanics, indeterminism is inevitable. Here's why. If the universe cannot store infinite information about its present state, then it cannot store complete information about how that state evolved from the past. Some details must be forgotten. And if the present doesn't fully determine the past, then by time reversal symmetry, the present cannot fully determine the future either. Indeterminism isn't mysterious, it's the inevitable consequence of finite memory. Second, the measurement problem. Why does quantum superposition collapse when we measure it? Why does observation force nature to choose one outcome from many possibilities? In finite precision quantum mechanics, the answer is clear. Measurement forces the universe to output information, to record a definite outcome. But recording requires memory. Since memory is finite, the universe must delete something to make room. What gets deleted? The information about all the other possibilities in the superposition. They must be forgotten so the one actualized outcome can be remembered. Wave function collapse isn't a mysterious process. It's strategic information management, reality deciding what to remember and what to forget when memory constraints force a choice. Third, the arrow of time. Why does time flow in one direction? Why can we remember the past but not the future? Why does entropy increase? The second law of thermodynamics says entropy, disorder, increases because there are vastly more disordered states than ordered states. Systems naturally evolve toward more probable configurations. But this never fully explained why time has a direction. The fundamental equations of physics are time-symmetric. They work equally well forward or backward. Gieson's framework provides an answer. Time has a direction because forgetting has a direction. The universe sheds information continuously as it evolves. The past contains more information than the present because some past information has been lost, pushed beyond the memory horizon. We remember the past because the past is encoded, partially, in the present. We don't remember the future because the future hasn't been encoded yet. It will emerge partly from the present and partly from new information that doesn't yet exist. By late 2019, Gieson had developed his ideas into a comprehensive framework published in Physical Review Letters. The paper carried a provocative title, Time Really Passes and Propositions Become Definitely True. The implications extended beyond technical physics. If Gieson was right, then the future is genuinely open, not predetermined. Time is real and fundamental, not illusory. The present moment is ontologically special. It's the boundary between determined past and undetermined future. Reality is fundamentally creative, generating new information as it evolves. But the evidence forces us to confront an uncomfortable possibility. We are living in a universe with cosmic amnesia, and that amnesia is what allows us to exist, to change, to have experiences at all. Act 2. Accumulating Evidence. Part A. The Limits of Memory. The first direct evidence that the universe has finite memory capacity came not from Gison's theoretical work, but from black hole physics, specifically from Stephen Hawking's discovery that black holes have temperature and entropy. In 1974, Hawking proved something shocking. Black holes aren't perfectly black. They emit radiation due to quantum effects near the event horizon, a phenomenon now called Hawking radiation. This radiation has temperature, which means black holes have thermodynamic properties. They're heat engines, subject to the laws of thermodynamics. And the second law of thermodynamics, entropy always increases, applies to black holes just as it applies to everything else. Black hole entropy is given by the Bekenstein-Hawking formula, S equals A over 4, where A is the area of the event horizon in Planck units. This formula reveals something profound. The entropy of a black hole, which measures how much information it contains, is proportional to its surface area, not its volume. For ordinary objects, information scales with volume. A larger hard drive stores more data. A bigger book contains more text. Volume determines capacity. But for black holes, and by extension for any region of space prevented from communicating with the outside by light speed limitations, information scales with boundary area. This is the holographic principle. The information content of any region is bounded by its surface area measured in Planck units, not by its interior volume. Jacob Bekenstein, who first proposed that black holes have entropy, calculated the maximum information density possible in our universe, approximately 10 to the 69 bits per square meter of surface area. This sounds enormous, but it's finite, and crucially, it imposes hard limits on how much information any physical system can store. For the observable universe, a sphere roughly 45 billion light-years in radius, the maximum information capacity is approximately 120 bits. That's a 1 followed by 120 zeros. More bits than there are atoms in the universe. More information than humanity has produced in its entire history by many orders of magnitude. But still finite. Still bounded, still insufficient to store even a single real number exactly. This finite information capacity has profound implications for how the universe operates. Consider a simple quantum system, an electron orbiting an atom. In standard quantum mechanics, the electron's wave function is a complex-valued function over continuous space. To specify this wave function precisely requires infinitely many numbers, one for each point in space, each point requiring infinite decimal precision. Infinitely many numbers, each with infinite precision, equals infinitely much information. But the universe can't store infinite information. So either A, the wave function isn't real, it's just a calculational tool, not an actual physical entity, or B, the wave function is real but approximate. The universe stores a finite precision approximation, not the infinite precision ideal. Gison's framework embraces option B. The wave function is real but discretized. The universe stores a finite approximation and discards the rest. Evidence for this comes from quantum computing research. When physicists build quantum computers, they encode information in quantum states, superpositions of qubits that can represent multiple values simultaneously. These quantum states are wave functions, just like the wave functions that describe electrons in atoms. But quantum computer engineers have discovered something frustrating. No matter how carefully they isolate their qubits, quantum information gradually degrades. Superpositions decay into classical states through a process called decoherence. The standard explanation is environmental noise, interactions with stray electromagnetic fields, thermal fluctuations, cosmic rays. The quantum system isn't perfectly isolated, so environmental interactions corrupt the quantum information. But even with extraordinary isolation, temperatures a fraction of a degree above absolute zero, electromagnetic shielding, cosmic ray deflection, decoherence persists. It's as if there's a fundamental limit to how long quantum information can be preserved, regardless of how well you protect it. In 2021, researchers at IBM discovered something remarkable. The rate of quantum decoherence in their most advanced quantum processors matched, to within experimental error, the rate predicted by Gissin's finite precision quantum mechanics. If the universe has finite information capacity and must constantly compress quantum states to fit within that capacity, then quantum information should decay at a calculable rate, exactly the rate IBM observed. The universe wasn't just limiting our ability to build quantum computers. The universe itself is a quantum computer with finite memory, and decoherence is its garbage collection process, reality forgetting details to make room for new information. But this represents just one piece of a much larger puzzle hidden in the structure of causality itself. If the universe forgets information continuously, then the past doesn't fully determine the present, and the present doesn't fully determine the future. Causality becomes probabilistic, not deterministic. And that has implications for the most controversial question in philosophy. Do we have free will? Part B. The freedom in forgetting. The free will debate has raged for millennia. Determinists argue that if the future is fixed by the past according to physical laws, then our choices are illusory. We think we're choosing freely, but actually we're just following predetermined paths. Libertarians, in the philosophical sense, not political, argue that humans possess genuine agency. Our choices are truly ours, not mere inevitable consequences of prior causes. The debate seemed stuck in stalemate. Either physical determinism is true and free will is illusion, or free will is real and physics is incomplete. Gissin's framework offers a third option. Physics is complete, determinism is false, and free will is real, not as some mystical property of souls, but as a direct consequence of the universe's finite memory. Here's the argument. If the universe has finite memory, then it cannot store complete information about the present moment. Some details, values with insufficient precision, correlations too weak to encode, information beyond the memory horizon, must be forgotten. This means the present state of the universe is not fully specified. There are degrees of freedom, aspects of reality not constrained by past history, because that history has been partially forgotten. When you make a choice, when your brain processes options and selects one, that selection isn't fully determined by prior brain states, because those prior states weren't fully determined either. At every moment, your neural dynamics include information that's genuinely new, not inherited from the past. Your choice is partly caused by your past, your memories, values, personality, the information that was retained, and partly uncaused, emerging from the genuinely indeterminate aspects of reality. This isn't libertarian free will in the traditional sense. It's not a soul making choices outside the causal order. Your brain is still a physical system obeying physical laws. But it's not deterministic causation either. The laws are probabilistic, leaving room for multiple possible futures. And crucially, which future actualizes depends partly on information that doesn't exist yet, on the genuinely new information that reality creates moment by moment. You don't have free will despite being physical. You have free will because you're physical, and physics is fundamentally indeterministic due to finite information capacity. Evidence for this interpretation comes from neuroscience research on decision-making. In the 1980s, neuroscientist Benjamin Libet performed famous experiments showing that brain activity associated with a decision begins several hundred milliseconds before the person consciously experiences making the decision. Many interpreted this as evidence against free will. Your brain decides before you decide, so your conscious choice is an illusion, just post hoc rationalization of what your brain already determined. But more recent research complicates this picture. A 2019 study at the Berlin Center for Advanced Neuroimaging used machine learning to predict subjects' decisions from brain scans taken before the subjects reported making conscious choices. But the prediction accuracy was only about 60%, better than chance but far from perfect. Even with complete access to neural activity immediately before a decision, the experimenters couldn't reliably predict what the subject would choose. If decisions were fully determined by prior brain states, prediction accuracy should approach 100% given sufficient neural data. The 60% accuracy suggests decisions are partly determined, hence better than chance, but partly indeterminate, hence far from certain. The brain state before a decision genuinely doesn't fully specify which decision will be made. Some information is lost, forgotten in the process of deliberation, and new information, genuinely novel, not present in prior states, emerges in the act of choosing. This aligns perfectly with Gissin's framework. Neural dynamics operate near the quantum classical boundary, where finite precision effects are most significant. Synaptic transmission involves ion channels regulated by quantum processes. Neural computation includes genuinely indeterministic elements. When you deliberate over a difficult choice, your brain explores multiple possible futures simultaneously, quantum-style superposition at the neural level. When you finally choose, reality collapses that superposition, discarding the unchosen possibilities. You literally forget the paths not taken. Your brain cannot store every detail of every considered option, so it remembers only the chosen path and a compressed summary of the alternatives. This forgetting is what makes choice possible. If your brain retained complete information about all deliberative processes, it would be overwhelmed, paralyzed by perfect memory of every unconsidered option. Free will isn't freedom from causation, it's freedom through forgetting, the liberation that comes from reality's inability to remember everything, creating space for genuine novelty to emerge. You are free not because you're separate from physics, but because you're embedded in a physical universe that cannot perfectly predict its own future. Your choices matter precisely because they aren't fully predetermined. They're acts of cosmic creativity, reality generating new information through your agency. But the implications extend beyond individual choice. If the present doesn't fully determine the future, then history itself is creative, an unfolding story whose ending isn't written in its beginning.
Act 3. The Creative Universe. Part A. Time's Arrow and Memory's Loss. If you could play the universe backward, reverse every particle's motion, flip every field's direction, would you see the past unfold in perfect detail? Classical physics says yes. Newton's laws are time-symmetric. If you know the present perfectly, you can calculate both future and past with equal precision. Quantum mechanics introduces a wrinkle. Measurement is irreversible. You can't unmeasure a quantum system. Wave function collapse picks out one outcome from many possibilities, and that choice can't be undone. But even quantum mechanics preserves information in principle. The wave function evolves unitarily, in a way that maintains total information content. Nothing is truly lost, or so physicists believed for decades. Gieson's framework challenges this. If the universe has finite memory, then running time backward wouldn't reconstruct the past perfectly, because the information needed for perfect reconstruction has been deleted. The past isn't fully encoded in the present. Some past information has been pushed beyond the memory horizon, irrecoverably lost, not just hidden or scrambled. This explains why time has an arrow. The future is different from the past, not because laws of physics are time asymmetric, but because information flow is asymmetric. Information flows from past to future, but incompletely. Each moment inherits some information from the previous moment and forgets the rest. Each moment creates some new information that wasn't present before. The future is partly determined by remembered past and partly creative, generated freshly. Evidence for this comes from an unexpected source: biological evolution. Evolution is often described as optimization, natural selection finding better and better solutions to survival challenges. But optimization implies convergence towards some optimal state, some final form that represents the best solution. Yet evolution doesn't converge. Life keeps innovating, keeps generating new forms, new strategies, new solutions. The biosphere's creativity seems inexhaustible. Why doesn't evolution plateau? Why doesn't it find optimal organisms and stop? The traditional answer involves changing environments. Organisms must evolve continually to keep pace with predators, parasites, competitors. But this just pushes the question back: why don't environments plateau? Gieson's framework suggests a deeper answer. Evolution is fundamentally creative because physics is fundamentally creative. The universe generates new information continuously, information that wasn't latent in prior states, information that's genuinely novel. Mutations aren't just random reshuffling of existing genetic information. At the quantum level, they involve genuinely indeterministic processes: cosmic ray strikes causing DNA damage, quantum tunneling in DNA replication, thermal fluctuations triggering chemical changes. These processes generate information that didn't exist before. The mutation that creates a new protein fold, a new regulatory network, a new survival strategy. This isn't just recombination of pre-existing possibilities, it's creation, reality inventing something genuinely new. And evolution never exhausts the space of possibilities because that space is infinite, constantly expanding through reality's creative forgetting and renewal. This reframes the relationship between past, present, and future. The past influences the present, but doesn't determine it. The present creates the future, but doesn't predict it. Time is not a rearrangement of eternal truths, but a process of continuous creation. Every moment is genuinely novel. Every moment brings forth possibilities that didn't exist before. Every moment is an act of cosmic authorship, reality writing its own story as it unfolds. This isn't mysticism, it's mathematics, the inevitable consequence of finite information capacity combined with the universe's refusal to compute, to stop evolving, to stop bringing forth the new.
Part B. The computational horizon. If the universe must forget information continuously to make room for new information, where does the forgotten information go? In computer science, deleted data isn't truly erased. It's simply marked as unallocated, and new data eventually overwrites it. The information persists until something replaces it. Does the universe work similarly? Or is deleted information truly destroyed, gone from reality entirely, impossible to recover even in principle? This question connects to one of the deepest mysteries in physics, the black hole information paradox. When matter falls into a black hole, it carries information, the specific quantum states of all the particles comprising that matter. That information seems to vanish behind the event horizon, inaccessible to outside observers. Then the black hole evaporates through Hawking radiation. Eventually, the black hole disappears completely. What happened to the information? Did it escape in the Hawking radiation, as quantum mechanics demands? Information cannot be destroyed. Or was it destroyed, violating quantum mechanics? This paradox has tormented theoretical physicists for 50 years. Gissen's framework suggests a resolution. Information is destroyed, not as violation of quantum mechanics, but as its proper functioning in a finite memory universe. Quantum mechanics, as traditionally formulated, assumes infinite precision, real numbered amplitudes, continuous evolution, perfect unitarity. In that idealized framework, information cannot be destroyed. But real quantum mechanics operating in a finite memory universe, must discard information. The lost information doesn't go anywhere. It doesn't persist in scrambled form, waiting to be decoded. It simply ceases to exist. Black holes are the universe's ultimate garbage disposal, places where forgetting is maximized, where information is deleted most efficiently. This might sound like a radical proposal, but it has precedent in computational theory. In 1961, Rolf Landauer proved that erasing information generates heat, the Landauer limit. Deleting one bit of information at temperature T requires dissipating at least kT ln of 2 energy as heat, where K is Boltzmann's constant. This connects information to thermodynamics fundamentally. Information isn't abstract, it's physical. And deleting it has physical consequences: heat generation, entropy increase, irreversible change. When the universe forgets information, it isn't just updating an abstract database. It's performing a physical operation that increases entropy, generates heat, makes time flow forward. Recent experiments have confirmed the Landauer limit directly. In 2012, researchers at the University of Augsburg built a system that erased single bits of information and measured the heat generated. The measured heat matched Landauer's prediction exactly, kT ln of 2 per bit erased, within experimental error. Information deletion is real, it's measurable, it's unavoidable in any finite memory system. And if the universe is a finite memory system, as the holographic principle demands, then information deletion happens constantly, everywhere, at every level of physical reality. This changes how we understand computation and causality. Computation isn't just state transitions, inputs mapping to outputs. Computation is creation and destruction. Each computational step generates new information, the output, and destroys old information, intermediate values no longer needed. The universe computes its own future moment by moment, taking its present state as input, applying physical laws as the algorithm, generating the next moment as output, and deleting information that won't fit in the next moment's memory allocation. We think of physical laws as eternal rules governing change, but perhaps physical laws are memory management algorithms. The universe is strategies for deciding what to remember and what to forget as it evolves. The future isn't contained in the past, waiting to be revealed. The future is created through selective forgetting. Reality making room for new information by discarding old information, moment by moment, ceaselessly, creatively.
Act 4. The ultimate questions. The most profound implications emerge when we consider what this means for the deepest questions in philosophy and physics. First, why is there something rather than nothing? Traditional answers invoke a creator, or quantum fluctuations, or mathematical necessity. But these just push the question back. Why a creator? Why quantum fields? Why mathematics? Gieson's framework suggests a different approach. Perhaps nothing is impossible, not because something must exist, but because existence is an ongoing creative process that cannot not happen. If reality is fundamentally computational, if physics is the universe running algorithms on finite hardware, then nothing would require zero computation, zero information, zero memory. But such a state is mathematically undefined. It's not that nothing is unstable and decays into something. It's that nothing is incoherent as a concept when reality is computational. Something exists because computation cannot be zero. Information cannot be absent. Memory cannot be empty. The universe exists because existence is what computation looks like from the inside.
Second, why do we exist? Not humanity specifically, but conscious observers in general. Why does the universe contain beings capable of reflection, understanding, experience? The anthropic principle says we observe a universe compatible with our existence because we couldn't observe one incompatible with our existence. True, but unsatisfying. It explains why we're here, but not why here is a place where consciousness can arise. Gieson's framework offers deeper insight. Consciousness might be the universe's solution to the information management problem. If reality must constantly forget information, it needs strategies for deciding what to keep and what to discard. Conscious observers serve this function. We extract meaningful patterns from noise, compress experience into memory, focus attention on relevant features while ignoring irrelevant details. We aren't accidents, we're information management systems, the universe's way of deciding what's worth remembering. Third, what is time? Is time real or illusory, fundamental or emergent, absolute or relative? Gieson's framework provides a clear answer. Time is the process of information creation and destruction. Time is what forgetting looks like globally. The past is real. It's the set of all information that persists in the present. The future is not yet real. It's the set of all possible information states compatible with the present, plus genuinely new information not yet generated. The present moment is the computational boundary, the instantaneous now where remembered past meets uncreated future, where information deletion meets information generation. Time doesn't flow because reality moves through time. Time flows because reality continuously forgets and creates, discards and generates in an endless cycle of computational renewal. Fourth, is the universe deterministic or indeterministic? Neither and both. The universe is deterministic in that physical laws constrain how states evolve.
but it's indeterministic in that those laws operate on finite precision states, leaving degrees of freedom unconstrained. Future possibilities are narrowed but not eliminated by past actualities. Reality is guided but not imprisoned by its history. This dissolves the ancient tension between fate and freedom. We're neither puppets of destiny nor agents of pure spontaneity. We're participants in an unfolding computation that's partly constrained and partly creative, shaped by past but not enslaved by it, generating future but not arbitrarily. Fifth, what is consciousness? This question connects everything we've explored. If consciousness is fundamentally about information management, about creating unified experience from diverse inputs, then consciousness is the subjective side of what information management looks like. When your brain decides what to attend to, what to remember, what to forget, these aren't just computational operations, they're experienced operations. There's something it's like to focus attention, to recall memory, to let details fade. Consciousness might be what forgetting feels like from the inside, the phenomenal character of information selection, compression, and deletion. You are not a static entity observing change. You are change itself, a dynamical process of continuous information transformation, experienced as the flow of consciousness through time. Conclusion. We began this journey asking about an error Nicholas Geeson discovered in the mathematics of quantum mechanics, an assumption that reality computes with infinite precision. Now we understand that assumption was wrong because it ignored reality's most fundamental constraint, finite memory. The universe cannot remember everything. It must forget continuously to make room for new information. And this forgetting, this cosmic amnesia, isn't a bug. It's what makes reality dynamic, creative, alive. Without forgetting, time wouldn't flow. The past would determine the future perfectly. Choice wouldn't exist. Our decisions would be inevitable. Novelty couldn't emerge. Everything would be rearrangement of eternal truths. Consciousness couldn't arise. There'd be nothing to integrate, nothing to select. Forgetting is what saves us from frozen determinism. Memory's loss is freedom's gain. The current scientific consensus remains cautious. Geeson's framework is gaining adherence but hasn't achieved universal acceptance. Many physicists prefer traditional interpretations, arguing we shouldn't abandon real numbers in physics without overwhelming evidence. But the evidence is accumulating. Quantum decoherence rates, black hole information paradox, the arrow of time, neural indeterminacy, all point toward fundamental information limits in physical reality. Within a decade, we'll likely have definitive tests. Quantum computers approaching the memory horizon should exhibit characteristic deviations from standard predictions. Gravitational wave detectors might reveal granularity in spacetime itself. Black hole observations could confirm irreversible information loss. The next generation of experiments will tell us whether reality truly forgets, or whether infinite precision somehow persists despite all evidence suggesting otherwise. But regardless of how the experiments turn out, the conceptual shift is permanent. We can no longer assume reality is infinitely precise. We can no longer take real numbers as physically fundamental. We can no longer ignore information limits when building physical theories. The universe is a finite system doing infinite work, computing the future from the past, moment after moment, never exhausting the creative possibilities because creation itself is inexhaustible.
We are participants in this cosmic computation, patterns of information that persist through time by forgetting and remembering, by discarding the irrelevant and retaining the meaningful, by making choices that matter because they aren't predetermined. The memory horizon isn't a limit, it's liberation. The universe forgets so that tomorrow can be different from yesterday. Reality loses information so that the future can contain genuinely new information. And you who are reading this, thinking about it, integrating it into your own understanding, you are the universe remembering itself, selectively, creatively, meaningfully. Every moment you exist is an act of cosmic memory management. Every choice you make is information creation. Every experience you have is reality computing itself into novelty. The universe is vast. The questions remain endless. The journey continues. But now we journey knowing what we are, not eternal observers of changeless truth, but temporary participants in endless creativity, patterns that persist by forgetting, beings that matter by choosing, consciousness that exists by continuously recreating itself from moment to moment. The horizon approaches, the memory fades, the future awaits.